Okay, so this is part of our first week of week 1 of our CSC 3710, which is our district structures, right? So I'm making a video on part of week 1 and possibly part of week 2. Okay, so I'm starting right here with the language of sets. The language of sets. So we have the word set was introduced by George Cantor. Wow. Who lived between 1845 and 1918. Okay. So, like I said in class, you use uppercase to represent a set. For instance, I may write A to be what? Set of. Now, also remember I said in class, you use curly brace, something like this, like a curly, like a block in C++. So if I represent A as set of even numbers, now it's going to continue to infinity. Now, instead of listing all of them, I said you use 3 dots. You use 3 dots, right? Now, always use uppercase letter to represent the name of set. Okay? Now, if small a, lowercase a, can represent any of the members of A. Now, we can say A is a member of lowercase a is a member of uppercase A. Obviously, here you can say 2 is a member of A because uppercase A itself contains all even numbers. Okay? And we cannot list all of them. So you have to use 3 dots, which is called ellipses. Okay? Now, there is what is called axiom of extension. That says a set is completely determined by what its elements are, not the order in which they might be listed. So if you write this, A to contain 2 and 3, and B to contain 3 and 2, then A is the same thing as B. It doesn't matter the order. 2 comes first here, followed by 3, and 3 comes first here, followed by 2. So it's still the same thing. A and B are same. Okay. That is it. And now you can see right here, this A contains what? One, two, three, and B contains 3, 1, 2. So A is the same thing as what? B, equivalent to B, right? Now, this is the first one here. This is quite easy, right? Here, they are telling us whether the notation set of 0 is the same thing as 0. The answer is no. The 0 at the right side here is just number 0, right? While this is just what is set. Let's look at it. Can you see? Now, look at, like I said in class, for the C here, you do not repeat element twice. So instead of writing 1 twice, you write only 1, 2, and 3. So A, B, and C are all same. Now for this B part, like I said, this one right here, it means a set containing number 0. is not the same thing as 0, which is what? In a number. All right. Okay. So, and the set here, look at that set. It contains number 1, which is right. Then is set 1. So if you name this set A, the first member of this set A is just 1. 1 is an element of A. Also, a set can contain another set. So set is a member of A. So that means this A contains sets as part of its element. Okay, for instance, you can list A to B again. It can have this 2 instead of just a number. Part of its member can just be another set. Do you see that? That is valid. All right, we've talked about all this in class. I don't have to discuss that again. Now, if you see this notation, if I write A is a collection of X in maybe N, such that P of X, what it means is that this set A is a collection of all natural number X, all natural number X, because this is for natural number. Now, you can use vertical slash, or you can use dot dot. But in this instance, I would prefer us to use slash, such that this statement P of X is true. This P of X is a statement, okay? Now, for instance, we have a R, which is a set of real numbers. Okay. Now, this obviously is open interval from -2 to 5. That is why you do not have less than here, okay? If you have -2 less than or equals to X, then this could have been a square bracket. In other words, you have to include this -2 and 5 as part of your element. But if you have strictly less than, if you have -2 less than X, that means you do not include -2 as part of your elements, and you do not include 5. So it has to be what? Open interval. This is an open interval. Okay, the same thing here. This is also an open interval. And let me tell you one thing. This one is telling us about all real numbers. All real numbers between -2 and 5, excluding -2 and 5. Okay, so you can list the numbers you have here is going to be uncountable. Remember, it's a real line, and between any interval, the number of real, the actual count of real numbers is going to be uncountable. For instance, if you have from 1 to 2, you can have 1.01, you can have 1.0001, you can have 1.214. You can keep listing them forever. You cannot exhaust the membership. Okay, that's that. And K for this one here, but yeah, oh, sorry. for this second one here, it's still open interval of integers. But this time around, we can list all the members completely. And this will give you -1, 0, 1, 2, 3, 4. See, you will never include -2, and you will never include -5. And when you represent it as an open interval, you have to use a parenthesis, not a square bracket. See how it's done? Again, the second one here should be straightforward, right? This is also an open interval because there is nothing like less than here. I mean, equals here. So that is what? A very strict open interval. And this will never contain -2. So you have to start to the right of -2, which is what? -1, 0, 1, 2, 3, 4. So, yeah. But we are not going to use negative because it's talking about positive numbers. So I'm sorry about that. So this will actually give us, this set will give you 1, 2, 3, 4. No, 5. 5 is not part of it. Okay, that's what you have. And let's check it. See what I got? Perfect. Look at it. And look at this one. Okay, so then we have the notion of subset, right? List numbers from 1 to 10, 8, 9, 10. Now, even numbers. Even. Let's use E to represent even numbers. We're going to do 2, 4, 6, 8, 10. And odd numbers will be 1, 3, 5, 7, 9. As you can see now, both you can find E and O inside E. So we can see that E is a subset of A. O is also a subset of A. That is it. It's a subset. All right. And that is what is called proper subsets and improper subset. Now, look at this definition. If A and B are set, then A is called a subset of B, which is written as what? If and only if every element of A is also an element of B. Look at this. We have an A here. Just this is mine that I made up myself. Okay, this is different from this one. This A, uppercase A, is the mega set. It contains the first 10 positive integers. Now, inside A, you have collection of even numbers and odd numbers. So this even numbers is a subset of A. So you can write subsets. Okay. So that means A, if A is a subset of B, that means A is contained in B. Okay. Right. I won't touch some of the slides. I'll just skip some of them. So I believe you can see them right here. Okay. And if you write this, means that there is at least one element X that belongs to A and is not in B. You see that? For instance, if my A is 1, 2, 3, 4, 5, and if my B is 1, 2, 9. You see, there is 1 here, there is 1 here, there is 2 here, there is 2 here. But there is 9 here, there is no 9 here. So we can say that B is not a subset of A. All right. So you can look at it. set A means a set of positive integers. Look at it, Z plus, right? And B, look at how your B is defined right here. Collection of integers such that 0 is less than or equals to that number, and that number is less than or equals to 100. Okay? So you are listening here. It means that your B start from 0, 1, 2, up until 100. We have to include 0 and 100 because of this less than or equals to. See, less than or equals to means you have to include the upper bound when you are listing them. Okay? So you can determine if B is a subset of A. So the answer is yes, because A here is bigger than B, right? So, wait, sorry. Oh, that B, sorry, B is not a subset of A because B contains 0. You can see right here, and 0 is never part of A. So you are looking at A as all positive numbers. You can keep listing, 3 dots. You can list them forever. And B contains 0. You can see our B contains 0. Therefore, B is not a subset of A. I'll skip some of them. Okay. Now, let's look at which of the following statements are true. This means 2 belongs to the set 1, 2, 3. That is very obvious because 2 is part of the members of this set. Okay, so this is right. This is true. This is false because this is a set, right? This set at the right side here contains only 1, 2, 3. So it doesn't contain another set. So this is wrong. That is false. 2 is a subset of this. That is right. This is not a subset of that. So yeah, this is right. And this is right. So we have true, false, true, false, true, true. So 2 are false and 4 are true. Let's see. You see that? Which is next one? False. This is true. False. See that? So C is false. I have, there's another one that is true. Okay. There's a lot of them. Okay. So that must have been some little typos over there. Okay. Now I move to Cartesian product. Cartesian product, remember in maths, if you have in a rectangle, if you have this side to be 4 centimeter and this side to be 6 centimeter, the area of this triangle is going to be what? 4 times 6, which is 24 centimeter square. All right. So when you have Cartesian products, okay, when you have a set, say it contains 1 and 2, look at the curly brace. Set B contains A and B. Do not write set as this, please. This is wrong. Now, Cartesian product, it's just a grouping element of set A, collection of all the elements from set A and B in an ordered pair manner. Okay, so, and it is written as A Cartesian product B, which is all you have to do. You can write your element of A as A1 and 2, and your B as A and B. You cross them right here. See that? Look at it. So this is for your what? A. This is for your B. And when you are doing Cartesian products inside this table, you have to use a parenthesis. So this is our A and 1, A cross 2, A, comma 2. See, I'm not using this. So you don't use set sign for Cartesian product. And this second one here is B1, and this is B and 2, B2. See, you cross A with 1, A with 2, B with 1, and B with 2. And that will give you, so Cartesian product of A and B is now a set of ordered pair. B1, B2. Now, Cartesian product is a set, okay? But the components or the members of Cartesian product sets are just ordered pairs or pairs of numbers. Look at it. So ordered pair, look at that word. Look at that word. Okay? And the number of elements of A in my example is 2. The number of elements of B is also 2. Look at it. I have 2 elements here. Now, the number of elements in Cartesian products will just be 2 times 2, which is 4. Right? Okay. So, right here, by definition, this one, it's not right. Because ordered pair 1, 2 will never be the same as 2, 1. Note, I'm using a parenthesis here, but if I use set notation, this is actually the same. Take notes. So there is differences between what? Set notation uses curly braces, ordered pair uses parentheses. All right. So this is no. Skipping some of them. So you can have, this is also no. See, this is also no. This is an ordered pair. So this is no. Look at the use of parentheses, right? It's no, right? So let's see example B. Is this one equals to this? Let's look at it. You have 3, 4, 1/2. And this is what? 3, 4, yeah, 1/2. So this is equals to this. So this is right. So these are same. All right. Okay. Okay. So this is correct. Now, Cartesian product generally, look at the way it is done. Given a set, different set A1 to AN, right? The Cartesian product of the set. Now, Cartesian product is just grouping elements of different sets together, okay? And look at the content. You need to use parentheses. So if I decide that my A is just 1, 2, 3, and my B is just X, Y, Z, Then my Cartesian product of A and B, I'll just do the table 1, 2, 3, X, Y, Z. I'll put the times here. So I'll group them. So X and 1, see? X1 is X comma 1, X2, that's X comma 2, X3. Inside the table, I am using parentheses. Y comma 1, Y comma 2, Y comma 3, and that's Z here. So Z comma 1, Z comma 2, Z comma 3. If you count everything here, you have 6, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And the Cartesian product that is derived from set A and B, we have 9 elements. The number of elements of A is 3. The number of elements of B is also 3. 3 times 3 will give you 9. Okay. So that is that. Note that when you do A cross B, it's not the same thing as B cross A. Please take note of that. Cartesian products are not. Cartesian products are not commutative. Are not commutative. Take note of that. All right. So look at this, for instance. Remember, the content here is not the same thing as 1x, because these are ordered pairs. But if you are using a set, remember, x1 will be the same thing as 1x for set. But for ordered pair, no. Okay? No. So I can't. I'll skip some of them. I can't. And remember, when you plot your graph of X and Y, so you have different points like that. This is called Cartesian plane. Cartesian plane. Look at that. It's called Cartesian plane. Okay. Right. And another important concept in our mathematics is what is called strings. Strings. It's called a string. Now, look at the word string. Given a finite set, when you say finite set, that means you can count all the elements in that set. Given a finite set A, a string of length n over A is an ordered n tuple element of A, written without parentheses or commas. The elements of A are called characters of the string. The null string of over A is defined to be string with no characters. It is often written as lambda and is said to have length of 0. Okay. Now, if I have A to be what? Collection of zeros and ones. Yes. Then the string over A. The string over A is called bit string. Because I can just generate, if I have bit string of 3, I will have all this. Now, when you are listing your bits, your string, do not put any bracket, parentheses around it. I can have 0, 0. I can have 1, 1, 1. I can have 1, 0, 1. I can have 0, 0, 1. I can have 0, 1, 0. These are just what? Bit string of each of length 3. Okay. Now look at the example right here. You have A to be A and B. This is a set. This is a what? a set. Now, the question says, list all the strings of length 3 over A with at least 2 characters that are the same. So I can have A, I can have A, B, I can have A, B, B. See, you can list them like this. See, A, B, A, B, A, B, A, B, B, A, B, A, B, A, B, 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 B. Those are the options you can have. And this is very, very important in programming. In computer programming, it is important to distinguish among different kinds of data structures and to respect the notations that are used. Okay, so you have to be very, very, very careful. This notation here in discrete mathematics is not the same thing as parentheses. Okay, this is a set. This is a what? Ordered pair, which are not same. They are different objects. Okay. Then I move to the language of relation. Language of relation. Now, in possibly your calculus 1 and 2 and pre-calculus, you must have heard about the word function or relation or domain. Okay. Now, let A and B be sets. A and B are what? Given sets. A relation R from A to B is a subset of Cartesian product. Okay, it's a subset of Cartesian product. And it's written as R is related to Y. Means that the Cartesian product containing X and Y are in that relation. Now, this is not real numbers, right? You have to be careful, okay? If I write X, that means that X is not related to what? Y. X is not related to Y. Okay, let's have an example. Let's have an example real quick. You have a set containing 1 and 2, another set containing 1, 2, and 3. Look at that. These are sets. They are what? Set. Look at the use of curly braces. Now, let's define a relation from set A to B as follows. In other words, if you have an ordered pair from the Cartesian product A and B, before you can talk about relation, you must talk about Cartesian product. Okay, that is very, very important. Now, so if you define these pairs as for X and Y to be in this relation, it means that differences between any of these two numbers must be an integer. Okay, it must be an integer. So if I pick X to be 1 from A, and I pick Y to be maybe 2 from B. Now let me look at this relation. That means X minus Y over 2. That will give me 1 minus 2 over 2, which is negative 1 over 2. This is not an integer. Therefore, that won't work. We can say that this is not a member of this relation because that made me I got 0. This is right. So this is correct because that gives me an integer. This is wrong because when I do X minus Y over 2 on this, I get negative 1/2. This is right. This is not right. Okay, look at it again. It's simply a relation. Once again, relation. Before you can define a relation, you must talk about ordered pair. Okay, ordered pair. So this is a relation because the differences between x and y over 2, divided by 2 here gives me 0, and 0 is an integer. But if you pick number 2 and 3, your 2 is x, your 3 is y, and you look at the expression x minus over 2, that will give us 2 minus 3 over 2, which is negative 1/2. So because we got a fraction, this is not a relation at all, according to this definition. According to this definition, okay? You can have many definitions. Let's look at another one. Now, this is a cycle. When you have something like this in mass, this is what? Equation of a circle. Equation of a circle, okay? So you can define a relation from R to R. Okay, let's have the definition. Define a relation from this R to R as follows. For any pairs of numbers in this Cartesian product, x, y is a relation in C, means that the square of x plus the square of y must give you 1. Must give you 1. So can we say that this number right here is a relation? If I pick this one, if I pick this number right here, if I pick 1 and 0, and I look for this my x, this my y, 1 square plus 0 square, it will give me 1, which is right. So therefore 1, 0 is a relation in C. That is correct. Let's see the answer. See, this is correct. But this is not correct because this gives me 0. And whatever I get here must be equal to 1. This is correct. This is not correct because the answer I got here is 4. And 4 is not equal to 1. Remember, whatever pairs you square and add together, the result must give you 1. That is the relation. You can make up your own relation. You can have as many as possible. Okay. And then I'm skipping some. So when you see something like this is the equation of a circle of radius 1. Of radius 1. Of radius 1. All right. So let's have another relation. Now, for every other pair in this, pair belonging to this means that x must be less than y. Now, if you pick up any relation, it means that whatever pair you have here, your x must be less than y. So and look at what we have here. If you look at this, this is your x, this is your y, this is x, this is y. Okay, you can draw a diagram for them. Now have that. So in this instance, this is 2, 1 is not a relation in S because this is x and y, 1 is y. And your x must be less than y. But our x here, which is 2, is greater than 1. So this is wrong. But this one is correct. It's because 2 is that. Why? Because 2 is less than 5. Your x must be less than y. So you can pick this, you can pick this, you cannot pick that. And we have function. We have function. The function f from a set to another set is a relation. Okay. If you have a set A, 1, 2, 3, and another set B is 2, 3, 5, 7. You can easily see that if this represents your x and this represents your y, you can see that y equals 2x plus 1. You would multiply everything here by 2 and you add 1 to it. That will give you this. Okay, so I am converting number 1, 2, 3. This one goes to 3. This one goes to 5. This one goes to what? 7. 2 times 1, 2, plus 1, 3. 2 times 2, 4, plus 1, 5. 2 times 3, 6, plus 1, 7. So this set is called domain. And while the output here is called codomain. Codomain. So you have domain A and codomain B. So one is input, your domain is the input, and your codomain is the output. Your codomain is the output. All right. So skipping some of them. You know, the textbook has got many multiple examples. Some I can't use everything in my video. I need to do one more before I stop the video. Okay. I love this example. This is a relation from S to S. And the relation is defined as this. The pair ST is a relation means that your T is AS. By appending, so if concatenation means you are appending string. For instance, if your string 1 is AB and string 2 is CG, then if you concatenate S1 and S2, you just join them to each other side by side, you have AB, CG. That is called string concatenation. String concatenation. Okay? String concatenation. And you can have many cool stuff. Look at it. This is a string. Remember, in a string, you do not put them inside a bracket. But if you want to find the length of them, how many members here? 1, 2, 3, 4, 5, 6. This is 6. Remember, you have to repeat, you have to count this as separate elements because it's a string. I am not talking about a set here, okay? Okay? In this, I have to rewrite this as A, B. If this is a set, then the length of this set is going to be 2. But with a string, you do not put, a string is assumed not to have anything around it. So if we have a string A, B, A, B, A, the length of that string will give you 6. The length of this string will give you 3. All right. So, and we have a function machine. Function machine. Function is just a processing machine. For instance, if I define a function mapping x to what? X squared plus 1. I can write this as f of x equals x squared plus 1. It's the same thing. In this notation, I'm using a mapping notation, where here I'm using a what? A functional notation. Functional notation. Okay, and what does that do? You have, if you have a function, defined as fx equals to x squared plus 1. If you have all your x as 1, 2, 3, that's your x. And then the outputs, you can call this output to be y. So you can call your f of x is this, right? You can also write, you can write it as y equals x squared plus 1. So you can call this y, which is the output. So what that means is that whatever element you have in the domain, if you square 1 square is 1 plus 1 is 2. 2, if you square 2, 2 square is going to give you 4. 4 plus 1 is 5. Then 3 square is going to give you 9. 9 plus 1 is what? 10. So as you can see, domain here is a set of the inputs. See? The domain is a set. And codomain is what? 2, 5, 10. Now, to jump from domain to codomain, you need a function to do that. You need a formula, a function to do that. That formula is a function, okay? And another name for domain is input. Another name for codomain is what? Output. All right. So you can read more about function, okay? You can read more about function. So a relation is a subset of a Cartesian product, while a function is a special kind of relation. Okay. Let me see. Then let me talk about power set as the last thing for today. Power set. Now, if I list a set A equals 1, 2. Power set of A. Power set of A is the collection of all possible subsets of A. Now, take note of this. This is very important. If you have the original set to be 1 and 2, now, what are the possible subsets of A? You can have empty sets is one of the subsets, because every set has got empty set as one of its subset. So empty set is one of the subset of A. 1 is one of it. 2 is one of it. You see that? Then you can have set of 1 and 2 itself. Look at what I have. Now, this has to be inside a set notation, because power set is a set of sets. Remember, power set is a set of sets. So your power set of A, let me call it power A, equals the collection of all possible subsets of A. The 1 is there, 2 is there. They must be in a set notation when you are putting them in a power set, and the original set itself. So I have altogether 1, 2, 3, 4, which is 2 raised power 2. Power sets of A contains 4 elements, which is 2 raised power 2. Now, take note of one important formula. Let me clean this up. Delete. Now, if a set A has m elements, take note of this. Then the power set of A will have 2 raised power m elements. This is very important. This is going to come out in many of the quizzes. Let me give you a question right now. Let's say A is a set of all prime numbers between 1 and 10. I have 2, 3, 5, 7. What is the cardinality? Cardinality means the number of elements. Cardinality of the power set of A. Remember, cardinality is another word for how many elements you got. So A, the number of elements of A is 4. So the power set of A, we have 2 raised power 4 elements, which is 16 elements. I'm going to stop my video here for tonight. I'm going to see you in class. Thank you so much and have a nice day.